I want to start by asking you, the listener, to think about how you adapt to new situations. Um, Say you are playing a traditional board game with rigid turn-based rules,
Right.
and
Okay.
then you switch to a video game. Maybe it has artificial physics, maybe gravity is reversed or something, or you just walk outside and navigate a crowded street. The rules change, the goals change, but you adapt seamlessly.
You figure out the underlying structure of that new world. I mean, it is a fundamental aspect of biological intelligence. We do not just learn a specific task. We learn the environment itself.
We build a mental model of cause and effect.
And we adapt our strategies to fit those dynamics. Humans are cross-environment learners by default.
But when we look at the AI agents we are building today, that adaptability is largely missing.
It is. The current paradigm is typically evolution within a single domain. If you train an agent to code, it evolves within a coding environment. Implicitly, these agents assume a fixed environment distribution.
So they optimize for a specific set of rules.
They rarely face the challenge of stepping into a world where the rules of logic or physics have fundamentally shifted.
Which brings us to the focus of our deep dive today. We are looking at a paper titled AutoEnv, Automated Environments for Measuring Cross-Environment Agent Learning.
The researchers identified a major infrastructure gap here. We haven't had a standard way to measure whether an agent can truly learn across different worlds.
Because we just didn't have a way to generate thousands of diverse environments efficiently. Our mission today is to unpack how this new framework automates the creation of diverse worlds to test that exact capability.
AutoEnv is essentially an automated factory for creating controllable environments. The objective is to see if agents can move beyond memorizing tasks and start generalizing their learning strategies.
Let's break down how this factory works. The paper describes AutoEnv as treating an environment not as a singular block of code, but as a factorizable distribution.
They break it down into 3 distinct layers. That factorization is critical for the experiments they run later.
The first one is the base env layer, right?
The base env is the bottom layer. It implements the core dynamics. That means the state of the world, the transition functions, so if the agent moves left, what happens mathematically, and the reward function. This is the underlying reality of the simulation.
Then sitting on top of that is the obsenv.
The observation environment. This is the policy regarding what information is actually revealed to the agent.
Like in a strategy game, the difference between seeing the entire map or operating under a fog of war.
That is a perfect comparison. It controls the information flow. You might only have partial visibility.
And the final layer is the stinenv.
The rendering layer. It converts those mathematical observations into agent-facing modalities. In this paper, those are primarily text or images.
So this allows the researchers to keep the underlying base env rules identical while completely changing the aesthetic presentation.
A game about resource management could look like a sci-fi trading post in one iteration and a medieval farm in another. The mathematically optimal strategy remains constant.
The generation process itself is quite interesting. The paper notes they can generate these environments very cheaply. It comes out to an average of $4.12 per environment.
They utilize a pipeline of coding agents to achieve that efficiency. It begins with an environment theme, which can be generated by an LLM or reviewed by a human.
Then this theme is converted into a domain-specific language.
And then coding agents write the actual implementation for those 3 layers we discussed. They also write a level generator and a validator.
So the AI is writing the code for the test that other AIs will take.
It even includes a self-repair loop. The coding agents run syntax and execution tests on the code they just wrote. If the environment crashes or fails to compile, they read the error message and iteratively fix their own code until it passes.
Writing code that runs is one thing, but writing a good test is another challenge entirely. You could easily generate a game that is impossible to win, or one where the outcome is purely random.
The paper outlines a 3-stage verification process to handle that. First is execution, which simply checks for crashes. Second is level generation, ensuring valid levels with reachable goals can be produced.
And the third stage is reliability, verified through something called differential model testing. This stood out to me as a very clever quality control mechanism.
They use a weaker model, specifically GPT-4 Mini, and a stronger model, DeepSeek v3.1. They have both agents play the generated environment.
The logic being that if the environment relies on skill and reasoning, the strong model should outperform the weak one.
If the weak model consistently beats the strong model, or if the scores are indistinguishable, it implies the environment is dominated by randomness or is simply broken. Those environments are discarded.
It filters out the noise. After running this pipeline, they established a dataset called AutoEnv-36.
That consists of 36 high-quality environments with 358 validated levels. They categorize these environments along 3 dimensions to stress test the agents.
Reward, observation, and semantics. I want to focus on that third dimension, semantics. They categorize environments as aligned or inverse.
This is where they test whether an agent is reading the manual or actually learning the world. In an aligned environment, the descriptions match common sense. Water puts out fire, medicine restores health.
In an inverse environment, the rules defy common sense. For example, poison restores health or water decreases health.
The hypothesis is that a truly intelligent agent should be able to ignore its pre-training bias, which says poison is bad, and learn the actual rules of the specific world it is inhabiting.
But initial evaluations on AutoEnv-36 showed a data anomaly. The agents actually scored higher on the inverse environments than on the aligned ones.
Which seems counterintuitive. You would expect the confusing environments to be harder. The researchers investigated and found it was an artifact of the generation process.
When the automated pipeline created inverse environments, it tended to make the underlying structure simpler to compensate for the confusing descriptions.
So the inverse games were structurally easier to win. To get a real measurement, they had to control for that structure.
They set up a controlled experiment called skin inverse. They took an aligned environment with standard rules and difficulty and used the skin env layer to invert only the labels.
The code for the mechanics remained identical. Only the text displayed to the agent was flipped.
For instance, in a field detection task, they displayed the value 3 as stable and 0 as critical.
However, the underlying mechanics treated 0 as the target. If the agent were truly learning the dynamics, it would notice that interacting with critical yielded rewards.
And the results of this experiment were quite stark. Performance dropped by roughly 68%.
That is a massive degradation. It indicates that current agents rely heavily on surface-level wording the semantic skin, rather than learning the underlying causal rules.
They read the label critical or poison and avoid it based on their training data.
Even if the immediate feedback from the environment explicitly rewards interacting with it, they are following instructions rather than observing reality.
This leads us to the second major component of the paper. We have the AutoEnv testbed. Now, how do we look at the agents themselves? The paper introduces a formal framework for agent learning.
They formalize learning as a component-centric process with 3 stages: selection, optimization, and evaluation.
Selection refers to choosing which candidate agent to improve.
It involves deciding whether to pick the candidate with the absolute best score, best selection, or to pick from a range of candidates that balance score and cost, known as Pareto selection.
Then comes optimization, which seems to be the engine of the learning process.
Optimization is the mechanism of change. They identified 2 main signals. The first is instruction-based. The agent analyzes its past trajectory, identifies mistakes, and rewrites its own instructions. It is essentially engaging in self-correction.
And the second signal is dynamics-based.
In this mode, the agent attempts to deduce the rules of the world. It looks at the interaction data and writes code or notes to map the environment. It tries to reverse engineer the base env layer we discussed earlier.
And the final stage is evaluation, running the new agent to see if it improved. They apply this framework to a specific case study in the paper called the agricultural simulation, also known as Backwards Valley Farm.
This environment serves as a prime example of inverse semantics. The rules are counterintuitive.
How did the different learning methods compare in this specific simulation?
When they use prompt-only learning, where the agent just refines its instructions, accuracy increased from about 0.25 to 0.47.
The agent prioritized actions like harvesting over planting.
It learned a better heuristic, but
Yeah.
not necessarily the underlying logic. But then they applied dynamics plus agent learning.
In that configuration, the agent implemented code to track statistics and rewards.
It built an internal tool to analyze the environment. By doing so, it cracked the counterintuitive rules because it was analyzing the data rather than the labels. This allowed it to exploit the reward structure where standard heuristics failed.
It suggests that for certain environments, you need tools to understand reality, not just better behavior.
This leads to the concept of the learning upper bound. The researchers calculated the best performance achievable if one could select the optimal learning method for each specific environment.
Looking at the experimental results across the entire AutoEnv-36 dataset, there is a clear stratification in model performance. O3 led the pack with approximately 48% normalized reward.
GPT-5 followed. while GPT-4 Mini struggled significantly, achieving only around 12%.
Even the best model is achieving less than 50% reward.
It demonstrates the difficulty of the benchmark. But the more critical finding concerns the learning methods. The paper establishes that no single learning method works universally.
Some methods that helped in one environment actually hurt in others.
For example, a method that improved performance on an environment called interdimension caused a performance drop on Backwards Valley Farm.
If you apply a dynamics-based learning method to an environment that is pure pattern matching without clear cause and effect dynamics,
The agent might hallucinate rules that don't exist. Conversely, using instruction refinement on a puzzle requiring precise calculation might lead to the agent simply writing better-sounding excuses for failing.
the statistics in the paper support this. A method that gained 8 points on a specific subset only gained 3 points when applied across the full 36 environments.
That illustrates the diminishing returns of fixed strategies. As the diversity of the environment distribution increases, the effectiveness of any single rigid learning method declines.
The paper suggests the solution is environment adaptive selection. This means the system analyzes the environment and selects the appropriate learning strategy.
Deciding whether to write code, refine prompts, or take another approach. They tested the effectiveness of this adaptive approach and found it substantially improves performance.
However, there remains a gap. The difference between the best single method and the adaptive upper bound is significant, approximately 5.35%.
This is referred to as the learning gap. It represents the performance left on the table because the agents are not yet capable of perfectly choosing the right learning strategy for the problem at hand.
There is also an interesting graph regarding the diversity of methods. It showed that adding more learning methods to the pool improves the upper bound, but the marginal gains shrink quickly.
Going from one method to two provided a large jump. Adding a fifth or sixth method yielded very little return. This suggests that simply adding more pre-scripted learning methods is not the ultimate solution.
The paper concludes with a perspective on where this needs to go. They argue that the future isn't just about better static models.
It requires systems that can automatically design and compose their own learning strategies. The agent would land in a new world, test the interactions, and then decide how to learn.
It moves from asking how to solve a task to asking how to learn to solve a task.
AutoEnv also opens the door for testing beyond text-based environments. The paper mentions multimodal settings, discussing the use of image generation models for the scalable.
That would allow for testing in embodied settings where an agent must interpret visual cues.
An agent might have to learn that a specific texture implies low friction, not because of its training data, but because it slipped when it stepped on that texture in the simulation.
That connects back to the skin inverse experiment. If we can generate visual skins where ice is sticky and sandpaper is slippery, we can test if an agent is truly observing.
It creates a disconnect between the training data and the test data that forces real-time adaptation.
I want to revisit the verification process briefly because the reliability check where the weak model competes with the strong model seems to have broader implications for how we generate data.
It implies that generating a balanced challenge is difficult. If a game is too chaotic, intelligence provides no advantage. If it is too simple, intelligence is unnecessary.
AutoEnv has to filter out a significant amount of generated content to find that Goldilocks zone where reasoning actually impacts the outcome.
The fact that they have to discard environments where the weak model wins suggests that automated generation produces a fair amount of noise.
But the resulting AutoEnv-36 dataset, while relatively small, is highly diagnostic. The low success rates of top models confirm that it is a rigorous test.
It exposes the brittleness of current methods. When a sophisticated learning method actively harms performance in the wrong environment, it challenges the assumption that more reasoning is always beneficial.
Sometimes, overanalyzing a simple pattern leads to failure. So for someone building agents, the takeaway seems to be that reliance on a single optimization loop is risky.
You cannot assume your agent's learning method will transfer. If you optimize an agent to self-correct code, that mechanism may fail when the agent is navigating a web browser or a game. Testing across heterogeneous rule distributions is necessary.
The agent effectively needs to be part of the selection process. It needs to be aware of its own learning process.
It must evaluate its rate of improvement and switch strategies if it is stagnating. That is the comparison the paper invites.
It is the difference between a student who blindly applies a study technique versus one who realizes the technique isn't working and adapts.
Currently, most agents are applying a single technique. We need them to become active, adaptive learners. AutoEnv provides the infrastructure to train for that adaptability.
It provides a standardized way to present agents with worlds they have never seen before and measure how quickly they can decipher the rules.
By automating the creation of these environments, the researchers have provided a metric to track progress toward true flexibility.
The mission of this deep dive was to unpack how this framework automates the creation of diverse worlds. It appears AutoEnv has successfully highlighted that while our models are powerful, they are still quite rigid when the fundamental rules of their environment shift.
We can see the upper bound, but we haven't reached it yet. Closing that learning gap will likely require the shift toward agents that design their own learning strategies, as the authors suggest.
I want to leave you, the listener, with that final thought. Think about a future where systems don't just rely on pre-programmed methods, but automatically design and compose their own learning strategies on the fly. That is the clear direction for future research.
It is a fascinating frontier.